We turn on the tap, water flows. Easy, right? But ever think about what it takes to get that water flowing, especially if you're on a well? It's like you wouldn't use a tiny straw for a super thick milkshake, right? Well, it turns out, design is kind of like that. It's crucial. So we're going deep on all the factors involved today, looking at your notes. And trust me, there's some real aha moments in here.
Yeah, well, design it's way more than just digging a hole and crossing your fingers.
So let's jump in. Our notes mention different types. Driven, drilled, open hole. It's not one size fits all.
No, not at all. The geology of your land, it really dictates what's going to work best. Like, imagine building a house without checking the foundation first. Risky, right? That's where pilot holes are key.
Okay, so they're like the soil test before the foundation. Tell me more about this crucial first step.
Exactly. It's a sneak peek at the soil and rock layers, which we, broadly categorize as consolidated or unconsolidated. Consolidated's like your bedrock, solid, like that pre-mixed milkshake, pretty consistent. An open hole well often works for that.
Got it. Open hole for easy geology. But what about when it's more complex, like, I don't know, trying to suck up a chunky cookie dough milkshake?
That's where drilled wells come in,
Wow.
with casings, screens, sometimes even gravel packs.
Yeah.
They handle those unconsolidated formations where it's more like loose sand or gravel.
Creating a stable way to, like, not get a mouthful of sediment.
Exactly. It's about efficiency, too.
Makes sense. So pilot hole tells you go simple or get complex with the design. Now let's focus on drilled wells since they seem pretty common. The notes mention different components. Casings, screens, pumps. Can we break those down? Starting with casing, what is that?
Think of the casing like the bodyguard of the well, a protective shell, usually steel or plastic. Prevents collapse, and it also stops any surface contaminants from getting down to your water.
So keeps things nice and clean. Now about those screens, those sound essential.
They are. Imagine a cylinder with, like, very precisely engineered slots. And these are placed at the bottom of the casing, letting water in, but keeping out that pesky sand and sediment.
So not a screen like for my window, more like a high-tech filter.
Exactly. And here's the kicker. Getting that screen design right is crucial. Too big, and you get that gritty milkshake situation. Too small, and the well's efficiency plummets because water can't get through.
All about finding that Goldilocks zone.
Yeah, and that's where those specific numbers in the notes matter. Engineers use things like entrance velocity, grain size analysis to get that slot size just right.
So they mess that up. The whole well's compromised.
It's like a house with a shaky foundation. Might work for a bit, but eventually problems. Bad screen means clogging, reduced flow, even premature well failure.
Okay. Starting to appreciate the precision here. We've got the casing, the screen.
Correct.
What about the pump? Where does that go?
Pump placement, another critical aspect, and you might be surprised to know there's debate about the best approach.
Oh, controversy. The notes mention this, yeah. Some argue for above the screen, others within. What's the deal with this pump placement puzzle? So where are we with this great pump debate? Above the screen or submerged within it?
Okay, well, traditionally, pumps were always above the screen. Kept them high and dry, less wear and tear from sand and sediment.
Makes sense, like keeping your, your prized possessions up high, away from dust bunnies.
Exactly. But here's where it gets interesting. Recent research is saying submerging the pump right within the screen can actually be more efficient.
Hold on, really? That sounds counterintuitive. Wouldn't it be more likely to get clogged that way?
You'd think so, right?
Yeah.
But studies are showing a well-placed submerged pump, it can create a gentler flow of water into the well. So actually less risk of clogging. Plus, being closer to the water source, the pump doesn't have to work as hard.
So it's a win-win.
Potentially longer lifespan, yeah. It's an ongoing area of research, for sure.
Okay, I see why there's debate. So we've got the pump placement. But there's more to it than just that, right? Our notes mention, like, grouting, gravel packs.
Right. It's not just about the well itself, but also what's happening around it.
So it's like, what, creating the right environment for the well to function?
Exactly.
Okay, let's unpack these other components, starting with grouting. What's the deal with that?
Grouting, it's all about creating a seal around the well casing. Like, imagine a snug-fitting jacket. Prevents contamination. Only water from the intended source gets in.
So no, like, pollutants seeping in from the sides.
Exactly.
Okay, makes sense.
Yeah.
And then gravel packs.
Gravel packs are especially important with aquifers that have very fine sediment. So remember those screen slots we talked about? Sometimes even the smallest slots aren't enough to keep out those tiny particles.
So the gravel pack's like a pre-filter.
You got it.
Okay, all this talk about protection.
Yeah.
What if things aren't well designed? What's the worst case scenario?
Well, it can range from, annoying things like reduced water flow
Hmm.
to more serious issues like contamination of the water supply.
Yikes.
And it's not just your well either. You have to think about neighboring wells.
Oh, right, right.
That's where well interference comes in.
Yeah, the notes mention that. So, like, my well is impacting yours. How does that even work?
So picture this. Every well creates this kind of like invisible cone-shaped dip in the water table as it's drawing water up. That's the cone of depression.
Okay.
It's a natural thing.
So, like, sticking multiple straws in a milkshake and you see those little dips around each one.
Exactly. Now, imagine those cones get too close, start to overlap.
Uh-oh.
That's the interference. Wells too close together, they start competing for the same water. The water table can drop, impacting everyone.
A resource war, but underground.
Yeah. And if it's not managed, you can have wells pumping air, damage, reduced lifespan.
Not good. So strategic placement is key.
Absolutely. Engineers use models to analyze the aquifer, figure out safe pumping rates, and most importantly, the spacing to avoid this interference.
It's all connected.
It is. But, protecting individual wells, that's one piece of the puzzle. We also need to think about source protection.
Right. So we've talked about protecting the well itself, but what about protecting the water before it even gets there? How do we make sure the source stays clean?
That's where time of travel comes in.
Time of travel. Is that like an underground GPS for water molecules or something? So we're talking about tracking the journey of water underground. Tell me more about this time of travel concept.
It's fascinating, really. Imagine you could follow a single drop of water as it travels through the ground, from a raindrop hitting the surface all the way down to the aquifer. Time of travel is about figuring out how long that journey takes.
Okay, so it's not literal GPS tracking, more like creating a timeline for that water's journey. But how on earth do they calculate that?
It involves a lot of detective work. Engineers use complex computer models, geological data to analyze the aquifer's properties, groundwater flow direction and speed, and potential sources of contamination on the surface.
So they're creating a map of potential contamination routes and how long it takes for water to travel along those routes.
Exactly. And here's why that's crucial. By understanding the time of travel, we can establish protective zones around wells. Think of it like a security perimeter for your water supply.
Like those circles they draw around a crime scene on those TV shows. Nobody crossed the line.
It's a similar idea. Our notes mention some real-world examples. In Waikato, there's a 30-meter inner protection zone around wellheads. Nothing that could contaminate the water is allowed within that zone.
That makes sense, like a safety buffer. But those zones aren't one size fits all, are they?
You're right. The size and regulations vary depending on the location, the potential risks. Our notes mention that in Canterbury, the middle protection zone extends a whopping 2 kilometers up gradient from the well. That's how seriously they take protecting those water sources.
2 kilometers, they're not taking any chances. So it seems like these protection zones, based on time of travel, are all about long-term thinking, ensuring we have clean water well into the future.
Precisely. It's about recognizing that groundwater is a precious, shared resource. Protecting it today ensures its availability for generations to come.
This deep dive has really opened my eyes to the complexity and importance of well design. It's not just about digging a hole, it's about science, engineering, and a whole lot of forward thinking.
Absolutely. It's a hidden world that most people don't think twice about, but it plays a vital role in our lives every single day.
Well said. And on that note, we'll wrap up our deep dive into the fascinating world of well design. If you want to learn more about the specifics we've discussed, be sure to check out the links to visual resources and additional information in our show notes. Until next time, stay curious.